right, we are continuing our discussion about X-ray diffractometry. I've titled this lecture XRD number 4, which I admit kind of sounds like a bad cologne. XRD number 4, when you want to smell like a yak. I usually start off the lectures with something interesting, a picture or something. And today, I guess the last lecture I started off with a spectra. Today, I'm starting off with an old appendix of physical constants that I got from B.D. Cullity's Elements of X-ray Diffraction from back in 1956. And if you look at other people's work, published works on X-ray diffractometry, they oftentimes steal figures from Cullity. And I've even shown stuff in the Brandon and Kaplan book, which is basically Cullity figure recolored. And I try to give credit where credit's due. Anyway, so physical constants, I thought this was quite interesting, and because they're not really units we use today. And this is getting to be a long time ago, 1956. And charge of the electron, so I learned the elementary charge of the electron to be 1.6 times 10 to the negative 19 coulombs. And here they have 4.8 times 10 to the negative 10 ESU. And I didn't Google it. I don't remember if I ever knew it, what ESU stands for. Mass of the electron, 9.11 times 10 to the negative 28 grams. Mass of the electron hasn't really changed much, but I learned it in terms of kilograms. Other kind of interesting units they have, they even have a unit for the electron volt. And, I always have learned the electron volt being the elementary charge times the voltage, basically. And so they give this in terms of ergs. So 1kx, and this comes back to us later on in this lecture. 1kx is 1.00202. I'm assuming this is angstroms. And so kind of interesting units that we no longer use today, but it's still pretty cool to look. And Boltzmann's constant, I'm assuming this is erg per degree angstrom, maybe. I almost sound more intelligent than usual, but I'm not very familiar with these units, but I kind of wanted to kind of show this to you all because it's kind of cool. People were doing science with different units, not too far away compared to now. So we're going to talk about 3 different XRD methods. This lecture is probably the most practical of the 4 that I give on X-ray diffractometry. I'll work on the basis of the satisfaction of Bragg's law in some way. So lambda equals 2d sine theta. Lau is the first ever diffraction method. The sample is stationary, and the X-ray wavelength varies. And I'm sorry it kind of carried over there, but the X-ray wavelength varies. Rotating crystal, so the detector and the source are held constant and the crystal moves. And powder X-ray diffraction, the X-ray wavelength is static. The sample is kind of static. Okay, it depends on the method. There's 2 different geometries that are used on your diffractometer setups. And so X-ray wavelength is static, the sample is static, and theta varies. And seemingly the most common analysis, although there are several Lau single crystal diffractometers, there's even one on campus, so I kind of should be careful with the statement I made there. But powder X-ray diffraction I do feel is the most common. Von Lau. We saw this in the previous lecture, and I didn't go into a great detail. And I did talk about calculating theta from R over D, but by convention, you always have to remember that the angle between your incident beam, or in this case it would be your transmitted beam, which is parallel with your incident beam, and your diffracted beam, so that angle is always 2 theta. And I explained it slightly differently why we report things in 2 theta in previous lectures, but here it's convention, and maybe it's a little more clear this way why we use 2 theta. But the angle between your incident beam, okay, and your diffracted beam is always 2 theta. So for Lau diffraction, if it's polycrystalline, you're going to get rings, and these rings are called Debye rings. If you're looking at a single crystal, you're just going to get spots, okay? And polycrystallinity is signified by rings on diffraction patterns. Later on, when we talk about electron diffraction, and we look at electron diffraction patterns, these kind of ring patterns are kind of a key that you've gone through dynamic recrystallization. So we'll talk about that a little bit more. Again, kind of pointing out by convention, it's 2 theta. There's back reflected Lau, and we saw that diagram in a previous lecture as well. And here's kind of a different representation of the same thing. So you shine your beam through your recording plane, in this case it's film, and it hits the sample, and then these back reflect. Here, however, the angle is pi minus 2 theta, and so it's a slightly different convention for the back reflection. All right, so let's work through a problem for Lau diffraction. And let me get my laser pointer. If you're a Zelda fan, you'll recognize this is a rupee. But right now it's our stand-in single crystal hunk of copper, and I know this is blatantly incorrect. I don't think a single crystal hunk of copper looks like this, but let's just humor me a little bit for the representation. So we have a single crystal hunk of copper. The distance d from your sample to the recording plane, this d, is 5 centimeters. You measure the first set of spots to be 6.17 centimeters, realizing, or maybe you have a table of lattice parameters, realizing that the lattice parameter of copper is 3.6 angstroms, and your X-ray source is cobalt K alpha, mixing it up a little bit, no copper K alpha today, cobalt K alpha, and you can look this up as well. We've also have provided tables and stuff like that on Blackboard. But the wavelength of cobalt K alpha is 1.79 angstroms. What is the plane that caused this first reflection? And you could kind of guess maybe just based on how things go, but perhaps it's texturized and the first reflected is not what you would expect. But let's go ahead and work through this. All right, so we're working through our Lau diffraction problem, and we've already kind of read it. And so we know our distance d is 5 centimeters, and the first radius is 6.17 centimeters. And so we want to recall, if I can make my pen work, there we go. So tan theta equals r over d, and that equals, in this case, 6.17 over our measured d, which is 5 centimeters. And if you actually look at a single crystal diffractometer, the distance to the recording plane is much smaller than the actual size of the recording plane itself. And so this already, I know it makes some sense. So 6.17 centimeters over 5 centimeters. So tan negative 1 of 6.17 over 5, I get 50.98 degrees. 50.98 degrees. And so that equals theta. It actually equals 2 theta. Okay, so if we, and I don't want to confuse anybody, but if you remember, this is actually 2 theta. Okay, so when we do the math, we're solving for theta, but we have to remember in our heads that by convention, it's actually 2 theta. So theta for Bragg's law is a 50.98 divided by 2. Okay, so the theta for Bragg's law is 25.49 degrees. It's 25.49 degrees. And so now we know theta. And so lambda equals 2d sine theta. And we're trying to figure out which plane caused this first reflection. Okay, that's what's being asked of us. Which plane caused this first reflection? And we know lambda equals 2d sine theta. We were told that we're using cobalt K alpha, and that's a 1.79 angstroms, and so that's going to be our lambda. And so now we're going to solve for d, okay? And so lambda over 2d equals sine theta, and so that means theta equals sine -1 of 1.54 angstroms over, oh, I'm a dope. We're solving for d. I don't know if I'll edit this out or not, because we already have theta. I don't know what I'm thinking. I made a mistake. D D equals lambda over 2. Lost track of what I was doing. Lambda equals D equals lambda over 2 sine theta. And so this equals, excuse me guys, or y'all, 1.79 angstroms over 2 sine of, and I got 25.49. And I get, sorry, a little boo-boo there. I get D equals to 2.08 angstroms. All right, so what do we have? We have an equation now. D equals A over the square root of h squared plus k squared plus L squared, okay? And some kind of practical things we want to kind of talk about. So this first reflection is going to be a first order. So it's going to be 111, 100, or 110, okay? And I didn't do that in order. I should have done 111, 110, you know, but anyway. It's going to be one of these 3 flavors, and it doesn't matter which one because it's all the same family. So we can try, let's try D, let's just try it. We'll try 100 for fun, and we know the lattice parameter is 3.60 angstroms. So we know D equals 3.60 divided by the square root of 1 squared plus 0 squared plus 0 squared. So 3.6 divided by the square root of 1. Always put the units. One squared is 1. All right, so 3.6 divided by, come on, calculator. 3.6. I don't. I'm laughing at myself. because I actually punched that in. And yes, I recorded it. So D equals 3.64100. And I didn't even need to calculate that, because if you remember, we said that in a cubic system, I'm trying to draw the repeat 110. 110 D equal to A. So if you remember that, you actually save yourself a calculation, because we already know that D is 2.08. So you can ask yourself, did I make this mistake on purpose for learning? Give me the benefit of the doubt, please. Let's just try D equals 3.60 angstroms over square root of 1 squared plus 1 squared plus 0 squared equals 3.6 over square root of 2 angstroms. And that's 2.54. Well, D of 2.54 is not 2.08, okay? So 2.54 equals not 2.08. So we know it's not 110. So we only have one choice left if we're believing it's a first order reflection. If in fact it's not a first order reflection, you have a lot more calculations to do, and there's actually computer software that does stuff like this. But we're doing it by hand because we're warriors, we're metallurgists. Okay, warrior metallurgists, that's my new Netflix series. So D equals 3.6. Oops, I'm so sorry. Divided by the square root of 1 squared plus 1 squared plus 1 squared. That's the square root of 3. And that equals, should be 2.08, or it's going to be a long night. .078 rounded up, 2.08 angstroms. So to answer our question, 111 caused it. If I had been a gambling person, I would have just picked 111, but it's good to go through the exercise. Hopefully this is informative. All right, the next flavor of diffraction that we kind of had on our initial list is rotating crystal. And a rotating crystal, so I got this also from BD Cullity. I used to show this kind of computer animation of rotating crystal, and it's kind of disappeared from the internet, which I kind of thought everything stayed forever on the internet. So I've kind of referred back to BD Cullity's excellent diagram of rotating crystal. And so if you look at this diagram, you have a hole in your film somewhere, okay, for the X-ray to pass through. And you have kind of a slit on the other side. So you have this almost 360-degree cylinder of photographic film in this case. And you shine your X-rays through, and this sample would be sitting on a stage and rotate somehow. And this is kind of cool. White radiation would be polychromatic. And so this was from filtered copper. I'm assuming copper K alpha. It's not really telling us which one. But again, for diffraction to be useful, okay, you need monochromatic waves. Polychromatic waves cause noise and interference and all kinds of things. And here, this would be the noise caused by polychromatic radiation. So it's actually kind of cool to see it visually on this older example. Anyway, rotating crystal, the specimen sits logically on an axis spins, and you have some sort of recording device, in this case photographic film, that's static, and you can analyze the diffraction pattern that way. Kind of cool. Dun, da, da, da. Powder X-ray diffraction. So I talked about different geometries of XRD instrumentation. This is a Bruker D8 Discover. It's the unit we have in metallurgy. We also have a Rigaku. And this Bruker system is usually set up for what's called Bragg-Brentano geometry. And the sample remains stationary during analysis. Parallel beam is what the Rigaku is set up as, and the sample moves during the analysis. For powder XRD, you can use solid and powder specimens. The Rigaku, I believe you can really only use powder. You take a microscope slide and put Vaseline on it, and then put your powder on the Vaseline. The Bruker has various sample stages, and so you have this, I believe it's a polycarbonate puck with a little hole in it. You can put powder there. A lot of people use it for solid specimens, and I've used it for solid specimens as well. And sometimes you have to get creative with how you stack up your specimen, and I'll show a picture of that. You can use solid and powder samples, proteins. You can look at single crystal specimens and polycrystalline specimens. Kind of looking at the geometry again, I had kind of a black and white, kind of oblong version of this same figure in a previous lecture. I got these figures from our Brandon and Kaplan textbook. And here again we see the Bragg-Brentano geometry, which is what we're using mostly in X-ray diffraction, at least on that Bruker system. And you have your source emits some X-rays. They're at the angle theta. We report things in terms of 2 theta. And I previously was saying, well, it's with respect to the source. Kind of the more elegant way to say it, it's the angle between the incident beam and your diffracted beam. And I always, again, I hate this one because it makes it seem like it's always going to be 90 degrees. That's not the case. But it's the if your X-rays could actually go straight through, this would be the incident beam, and 2 theta is again the angle between the incident beam and the diffracted beam, and also still with respect to the source too. I like this. So if I can go in person and show you this someday, I will. And I have basically a piece of fluorescent paper, for lack of a better term, and you can see the shape of the beam on this fluorescent paper. I usually turn out the lights, and so this is my substitution for showing you on a fluorescent piece of paper in person of the effect of slits. And I'll show you the example of slits later on in this lecture for our particular instrument. But this shows the effect of slits on the beam shape. And so this is the maximum width of a beam, and it'll occur at different angles for different slits. And so for this bigger slit, the angle at which the beam is the widest is lower than if you have a smaller slit. And the overall width of the beam is smaller for a smaller slit. Here you get more signal, but you also get more noise. Okay, so a wider slit, more signal, more noise though. Okay, so it's almost like an aperture. And I can stare at this light and I'm getting more signal overall, but I'm also getting more noise. I don't know if that's a good analogy. Smaller slit, you get a smaller signal, but you also get smaller noise or less noise. And sometimes you can obscure peaks by having wider slits. So don't forget that. Remember what I'm saying. With wider slits, you get more signal, but you can actually obscure peaks. So multiple peaks may appear as one. You can resolve more peaks with smaller slits, but your signal is less intense as well. And anyway, so bear that in mind. Don't forget it. Commit this to memory, and you'll be fine. All right, X-ray detectors And let me get my laser pointer again. So the early obvious X-ray detector was a photographic film, and recording in this case of the diffraction pattern would have been in spots. And excuse me. And we've seen several examples of X-ray diffraction patterns now. Maybe not several, at least two. One a Lau version, and another one the rotating crystal, of where you see these dots. And these dots were essentially recorded on a photographic film. And the X-rays interact with the emulsion, kind of just like developing regular photographic paper. And the diffraction patterns appear as black dots on a negative. And is that correct? On a negative. Anyway, fluorescent screens. Fluorescent screens are actually really good X-ray detectors, and I do have a fluorescent piece of paper, or a fluorescent screen again that I use to kind of look at the beam. If you're casting a diffraction pattern on a fluorescent screen, you would logically have to have some other way to record it. So you would use this in conjunction with a camera. I don't know why it took me so long to think of camera, but you would use a fluorescent screen in conjunction with a camera, and then you would take a picture of the fluorescent screen. A gas tube. So now we're getting into early electronic signal detectors, and so going from photographic film and fluorescent screens to a gas tube is kind of going from looking at spot patterns to a spectra. And the X-rays ionize the gas within the tube, and electric current is detected. And so that means it's being plotted. And so you have current peaks detected with respect to 2 theta, and those peaks are your diffraction peaks, basically. A scintillator. So this actually used to be a test question on old school tests. I would always say my favorite word is scintillating. And a scintillator, so the X-rays hit this scintillating material. That actually causes the ejection of a visible photon, which then hits a photocathode, which emits an electron. And this cascading electron effect is the principle behind a photomultiplier tube. And I really do like scintillators. We see scintillators time and time again in our equipment. And a electron detector is also a scintillator as well on scanning electron microscopes. And I borrowed this diagram from Wikipedia to kind of talk about it. So we have a high energy photon, which is an X-ray. It hits our scintillating material, which ejects a low energy photon, which hits this photocathode, which then entails the emission of an electron, which then goes through this array of diodes, if you will, and the signal is essentially amplified. And so that's the principle behind a photomultiplier tube. This kind of increase in electrons is called cascading electrons. So photomultiplier tube, 1920s technology, still used today, is in the form of secondary electron detectors on scanning electron microscopes. Could also be used as an X-ray detector. Anywho, solid state technology, so a silicon strip technology, and that's very, very similar to a CMOS image sensor. And if you've not seen me give lectures about CMOS image sensors, you've missed some that I've done this semester. But a CMOS image sensor, I'm taking this lecture with a CMOS image sensor, and there's one on my phone. The brother or sister, depending on if these things have genders, I don't know if they do, would be a CCD, charge coupled device. So solid state, silicon strip technology, it's a pared down, if you will, CMOS image sensor. It's a very simple PN junction, and CCD, charge coupled device, can also be used as an X-ray detector. And if I didn't make it clear, the transition from using photographic film and fluorescent screens to using a gas tube and this type of stuff is going from, let me see if I can just draw on it on don't know if it'll let me. Oh, it won't. Going from looking at spot patterns to spectroscopy. And so single crystal X-ray diffractometers are definitely spot pattern instruments. They're not spectroscopy instruments. But anything using a gas tube scintillator, solid state technology, or a CCD is a spectra, is using a spectroscopy. Sorry. All right, so XRD, X-ray diffraction. The powder samples give more of a signal, and so some people swear by taking a solid specimen, crunching it up, and then analyzing it that way because you get more crystals. You can get a lot from X-ray diffraction, so you can get an idea of crystal structure, phase identification, preferred orientation, the presence of cold work, particle size, and alloy composition. And that kind of goes with phase composition, with phase identification. But it's a little bit more than that for alloy composition, and I'll talk about that in a little bit more detail. Texturizing. With texturizing, you can tell the orientation of your specimen, okay, and that'll become more clear on these next slides, not just this one. And so I'm kind of showing this one, and here your specimen's oriented so that 111 can actually diffract, can actually show a peak. Here, because of the orientations, this is single crystal, right? You can't see these other peaks, so you can't see the 200 or the 222. Sorry, yeah, 220, 200, and 220 planes, just because of the orientation. You can see 222 simply because 222 is just the half step of 111, because so it's pretty much the same orientation, and you can't see 311 either. Okay, if I chopped it all up, if I took it and crunched it all up, I would have these crystallites, if you will, these polycrystalline sitting at all different orientations. So some of these little crystallites, if you will have the orientation so that they can be seen on this diffractometer. Okay, so single crystal versus a polycrystalline, you'll see more peaks with polycrystalline. You'll see more reflections, if you will. And we're kind of using this to get into texturizing, okay, using this example. If you look at this paper, and I've posted this paper a long time ago, the metal fabrication additive manufacturing using laser and electron beam melting technologies by Murr, you can see that they looked at a vertical plane and a horizontal plane, and they used two different planes. We've seen analogies to this talking about metallography, so you can make the metallography cube, and so you can see longitudinal transverse, that kind of thing. And so I'm struggling to remember what they mean by vertical and horizontal plane. I'm going to say they built a cylinder, and the horizontal plane maybe was looking at it topwise, and the vertical plane was looking at it here. Either way, there's a difference in the texturization between these vertical and horizontal planes, and there's actually two things I want to point out on this slide. So one is the difference in texturization. So for this horizontal plane, 110 was not as intense as it was on the vertical plane. And so you could say that on the vertical plane, your microstructure essentially, or your crystallographic orientation, was texturized to be 110. In the horizontal plane, that wasn't quite the case, and you could almost say it was texturized for 200. Okay, it's kind of cool because this was selected laser melting, and this N2 argon means that the powder used to make the specimen was gas atomized using the nitrogen as an inert gas, but the building of the component, the laser, so SLMs need an inert gas to fabricate a specimen. Okay, so it's either argon or nitrogen, are the two inert gases that are generally used. Electron beam melting takes place in a vacuum, so you don't need an inert gas to fabricate. You can cool it in inert gases, that's another story. So the powder was processed with nitrogen, but the build occurred in argon. Here, and this is both 17-4 stainless steel. So here we see two other things occurring. Okay, so we see differences in texturizing. Okay, so we don't see 111 at all here. Okay, but we see 111 here, but we see 111. We don't see alpha iron or alpha ferrite. We see austenite here. Okay, and so this is the powder was made in nitrogen, and the build occurred in nitrogen. Okay, in a nitrogen inert atmosphere. And so this austenite was not expected to be there. Nitrogen thermodynamically stabilizes austenite. Okay, so we're seeing the use of X-ray diffraction to do two things on this one. Okay, one, we're identifying the phase austenite, which wasn't expected to be there, but we're also seeing some texturing. And so we see 111 oriented austenite on the vertical plane. We don't see 111 oriented austenite at all. Okay, so there's some texturizing occurring and also some phase popping up. Okay, I put here this kind of tip for practical X-ray diffractometry. Okay, so when you compare peaks, it's actually best to normalize your peaks by dividing the intensities of all the peaks by the most intense peak and then reporting it as a percent. Okay, and so that's recording the relative intensity. Reporting the absolute intensity is kind of goofy, and you can see they just reported counts. Okay, there is a lot of machine-to-machine variability. Some people do their work with copper K alpha. Some people do their work with cobalt K alpha. So it's better to report your data relative to itself, if you will. Okay, so I kind of put this as a reminder to kind of show you guys, show you all some sort of practical use. And so here we have kind of interesting stuff. So we're seeing unexpected phases. We can chemically understand why nitrogen thermodynamically stabilizes austenite so it survives the SLM process. We also see some texturizing of the phase. And here we see texturizing of just iron, basically the alpha iron. JCPDS card. So I borrowed this from someone else's slide, and it's not even JCPDS anymore. But I put this because this is how I did diffractometry as a lad, and we had books. And so nowadays, everyone has the ability to go into these electronic databases and look everything up. And in our instrument in metallurgy, we have a separate computer that we look it up with now because of the licensing. And so knowledge is power, the old adage. Well, controlling diffraction data is also power. And so it was the Joint Committee on Powder Diffraction Standards, JCPDS. There was even ASTM cards at one point in time. And this was replaced by the International Center for Diffraction Data in 1978. And before I go to what it's called now, we'll just kind of take a look at what was on a JCPDS card back in the day. If you had a JCPDS card and it had a star, that meant it was a good card. This is halite or sodium chloride. This is kind of telling you some stuff. It also tells you where it came from. So it was recrystallized twice from hydrochloric acid. Well, okay, that's nice. Somewhere it tells you copper K alpha. So this is the card for copper K alpha. It tells you the different reflections. So the first reflection they saw was 111. The second one they saw was 200. And it tells you the different D spacings. Nowadays, it's a ICCD, so the International Center for Diffraction Data. It costs a lot of money to get the licenses to use these databases. And so kind of bear that in mind. There's also free resources, and I think I'll proliferate those to students as well, but it's not in this lecture. But so ICCD. Now, so we pay a license fee to ICCD, and then we get very similar data to what was on these JCPDS cards back in the day. And so you have it in a PDF type database. It's actually really, really useful. And so here's the material, or the card, if you will, for tellurium. and tellurium may not have been the best one because of the crystal structure compared to cubic crystal structure. But anyway, this has an A and C parameter, so it's very, very nice. And the way we identify our materials is basically a lookup system. You get a spectra on your sample and you compare it with a library spectra. And then you can also compare stuff to different cards, so you can calculate your own despacing and see if your sample matches what's in the database. So spectroscopy, in a lot of ways, is comparing with lookup tables, basically, or known data to figure out what you have. And we'll see some examples of using known data to figure out what you may have in a little bit here. The effect of strain, and let's see, I think this is trying to animate. It's my Playmobil, or my son's, actually it's mine, I have to admit it, my son's Playmobil set. And so if you have no strain, and this is really locking up my system a little bit. If you have no strain, your diffraction line is where you expect it to be. If you have uniform strain, it's shifting to the left. And if you have non-uniform strain, like what my blacksmith guy is doing here on my kitchen counter, you get peak broadening, okay? And you also get a lower intensity as well. And you can figure out the amount of strain induced on your specimen by this equation below. And I'm struggling to get my laser pointer to move down there. I did not expect. I'm running with a lot of RAM and stuff like that. Uniform strain would be like in a tensile test machine. So if I stretch it and don't break it, throw it in my XRD, I should see a peak shift to the left if I did that. If I bang it with a hammer, I would see peak broadening. Beta is peak width, and it's peak width in terms of 2 theta. Theta here is just your peak center divided by 2, okay, because we're getting 2 theta, right? And so and K is some constant, and we'll see later on the constant K is generally arbitrary. It's generally 0.9. Lambda is your wavelength, and D would be your crystallite size or your grain size. So there's ways to calculate strain based on diffractometry data. All right, so Z displacement is very important. I borrowed this slide from someone else, but it's a pretty well done slide. And the point of the matter is, if your Z displacement is low, your peak's going to shift to the left. And so it's very, very important that you get your sample height correct, because other shifts to the left are non-uniform, are uniform strain. Excuse me, I even put it here on the slide, uniform strain. And there we go, now my mouse is back. Excuse me, I'm sorry. Anyway, there's some math and stuff, but the point of the matter, the important thing is if your Z height is too low, your peak will shift to the left. And it's important that you understand that and not get it confused with uniform strain. If your sample is too high, you just won't get a signal for the most part. Particle size. So you can calculate particle size for XRD spectra using the Scher equation. And this Scher equation is very similar in form to the strain equation. I hesitate to go back to the slide with my animated GIF, and I'm having a little bit of computer trouble. But this equation here is pretty much the Scher equation, except we're squaring things. Now let's see if I can move to the slide I care about. Yes, the slide I care about. I love you, slide I care about. So the Scher equation, beta is the peak width equals K lambda. Again, K is an arbitrary constant. A lot of times it's just 0.9. D is your crystallite size or your crystallite diameter. Cosine theta. So theta is 2 theta divided by 2. B is the peak at full width half maximum. So, but you use the 2 theta width. You don't ever divide it by 2. I've had people tell me and argue with me, but they're wrong. Full width half maximum is always calculated using the 2 theta scale. Why? Because this is a spectroscopy exercise. Okay, so we're actually measuring the Will width of our peak. And so FWHM, full width half maximum, you need to convert it to radians. So you get 2 theta degrees. So degree times pi over 180 equals radians. If you forgot, one time in my life I forgot and I was schooled. We won't go into that. D is particle diameter. Lambda, of course, is your X-rays, the wavelength of your X-rays. So if you're using copper K alpha, that's your lambda, 1.54 angstroms. Okay, so it's going to typically be in angstroms. Here's another depiction of full width half maximum, and if you're using smaller slits, sometimes you can resolve stuff like this, these kind of doublet peaks. And this could actually be 2 substances, 2 phases, 2 elements. And if you look at the scale, we're at 46.7 degrees on the 2 theta axis to 47.9. Very precise XRD is. So again, here you're measuring the full width half maximum. Full width half maximum, if I didn't explain it, it's the width of your peak halfway to the top. And sometimes it's hard to figure out where you measure your bottom to the top from. So it's important to get rid of noise. And let's work out a problem talking about particle size, shall we? All right, so here's an example Scherrer equation problem that we want to work out. And I didn't talk about it in on the previous slide, so I should probably go over it again, and or at least read it to you. And you're examining an unknown powder in the XRD. You're using chromium K alpha radiation, so that's interesting. You can see my spell check kicking in, or grammar check rather. A prominent peak is observed. I guess it wants me to say was observed at a 2 theta peak of 38.25 degrees. The full width half maximum of the peak is observed to be the distance between 37 degrees and 39.5 degrees, meaning that B beta is the distance, or the 2 theta distance between 37 and 39.5 degrees. That's quite wide. What is the particle diameter of the gold powder? And well, there's some things that we need to kind of go look up if we don't have them readily available. And so we have tables that we've been given. And so we can say, if a handy pen turns on, chromium K alpha is 2.29 angstroms, thereabouts, 2.29 angstroms. I sincerely hope you can read that. What else do we need? I think that's all we need to know to solve this. So we want to write out, or we want to figure out beta now. And well, it's actually good engineering practice to write the equation that we're gonna use. So let me kind of stop right there and do that first. So we're solving this using Scherrer's equation. And so that's beta, the 2 theta beta, or 2 theta peak width, equals K lambda over D cosine theta. All right, so let's just say K equals 0.9. It's an arbitrary constant, usually 0.9. And some other things we need to kind of think about. We can rewrite it to be D equals K lambda over beta cosine theta. And when we plug and chug everything, we can get our particulate diameter of our crystallite diameter of our gold powder, if you will. Full width half maximum. So let me see, 39.5 minus 37 is the first thing we want to do, times pi over 180 to get it to radians. And by my math, I get 0.043 radians. We can then plug and chug everything in here. And so D equals 0.9 times 2.29 angstroms over, we have our beta in radians, 0.043 cosine and 38.25. So theta is 2 theta is 38.25. That means that theta needs to be divided by 2, or 38.25 divided by 2. So that's 19 point, we'll just say 19.13. So cosine, so plug and chug away, 2.29 times 0.9 divided by I got about 50.73 angstroms. And work along. If you got something drastically different, send me an email. But I think this is close. All right, from Cullity, and we didn't work out but one problem for full width half maximum and Scherer's equation. But if you didn't deduce what crystal size does to you, if you have a smaller crystal size, your peak begins to broaden. I like this because, you know, Cullity, it was before texting like OMG and LOL. So FWHM, you know, they just said half max. You know what I mean? They didn't do any of those fancy acronyms. You know, Cullity probably had impeccable thumbs because he didn't text. Anywho, smaller crystal size, broader peak, larger crystal size. This may be somewhat of an exaggeration. I like how it says schematic. But anyhow, larger crystal size, more narrow peak. That's the effect of crystallite size on your spectra. Chemistry and composition. So let me try to get my pen to work if I can. I don't think I can. Let me see if I can go, and I'm real sorry you're watching me do this live. Let's see if I can do it this way. There's different ways to determine composition from XRD data. Most of them involve a standard. And let's see, I can draw. Okay, so let me erase it. I'm embarrassed, but I'm not going to edit this out, I don't think. There you go. Okay, so if we look at point 1, and this is just intensity, okay? If we look at point 1, we're just going to have alpha. If we look at point 2, okay, so this is 1. If you look at point 2 now, and I won't do them all, but you can get the picture. We have alpha and some beta, right? And the overall intensity of the alpha is going to be less. Okay, and then we'll have a smaller peak of beta on the 2 theta. And I got these equations from Metal's Handbook, and there's other people that publish this similar types of equations. But there's different ways to determine composition from XRD data. Most involve a standard. This is, I need to redo this, I'm sorry. This doesn't look very nice. Can I erase it? I can erase it. Okay, so let me draw this again. So smaller peak for beta. and the intensity of this alpha peak is diminished with the pure alpha version. Okay, so one flavor is you can determine the weight fraction of A and the weight fraction of B based on the intensity of your A peak and the intensity of your B peak. And let me bring my laser pointer and see if that makes it more clear. So XA, XB, if you remember, you have XA, XB, right? But XB, and let me go back to pen. I'm sure this is fun for you to watch. I'm sorry. If you remember, XB equals XA minus 1. Okay, so you can solve it without having a system of equations, if you will, because you could just substitute one or the other. Okay, so you could find the weight fraction of one, then you figure out the weight fraction of the other based on comparing the intensities of the two peaks. Okay, and K is the ratio, so you would have to know what a 50-50 alpha beta or AB composition peak looks like. Okay, and then you multiply that by that becomes your K, and then you would take this ratio, so you would have this intensity divided by this intensity, multiply it by the ratio of the same substances when they're mixed 50-50%. And I hope, hopefully my words are not confusing you. If my mouth is confusing you, hopefully the text is a little bit more sensical. Okay, and let me erase this because I have an animation coming that I'm pretty sure is going to go right over that. So let me, all right. Another example where we have, we're taking into account the mass absorption coefficients, and this one's a little hooky. Again, I got this one from the Metals Handbook as well, volume 10 on materials characterization. And I didn't use the example of alpha and beta. Here I use cementite and pure iron. Okay, so X would be the weight fraction of cementite, so it would actually be what you're trying to solve for because we don't know how much cementite is in it. Mu over rho would be the mass absorption coefficient of cementite. Intensity pure would be the intensity of a sample of pure cementite, some sort of standard. And I would be the intensity of a cementite in your specimen. Okay, so if I had, I'm going to make another kind of example here. If I had a spectra and, wow, it actually gave me peaks, and I didn't mean for it to give me peaks. That's funny. All right, we have a spectra, and then we have our intensity, and this is, you know, in our specimen, and this is pure, and then we had other stuff in this one, right? We would do the ratio of the intensity of our Fe3C in our specimen to the Fe3C in, to a pure sample of Fe3C, so that would be this ratio. The mu over rho of cementite divided by mu over rho of our mixture, then we can solve for X. The trouble with this specimen, or this methodology, is, and let me just write it with the pen, is that you have to know the mass absorption coefficient of your specimen. So I found this a little nonsensical, because how would you know the mass absorption coefficient of your specimen if you're trying to figure out the amount of your mystery phase, okay, or your whatever phase you're caring about? Thought it was kind of goofy. I bring this up because I've been tasked before to tell people if stuff's alloying based on X-ray diffraction data, and it's not quite as straightforward as people think. You have to know some stuff, and you have to have standards on your material system. Okay, so it's kind of good rules of thumb, if you will. Another phase composition method, and I bring this up because XRD standards are made out of corundum, and corundum is alumina, and it's white alumina. Okay, the other flavor of alumina is sapphire, And sapphire is blue. It's a beautiful gemstone. You can dope it with titanium and other stuff, and you can maybe get some other different color variations and richness of the blue. But alumina corundum is basically the same stuff you polish metallographic samples with. However, it's a solid block, or probably a compacted block with multicrystallites, right? And so you could figure out another phase composition method. And so if you're interested in phase A in a global specimen, okay, the weight fraction of A can be found by this equation, 0.5. IA is the intensity of your peak A on the spectrum versus the intensity of corundum, specifically the 111 peak. Okay, so you have to be looking at a cubic specimen, right? So the ratio of the 100 peak to the ratio of the 100 from your standard, your corundum standard. This is another thing though, right? So if I have this new material system that no one else has done work with, it only works if I know the published ratio of the intensity of 111 of your phase of the 100 peak, excuse me, it's right in front of me. I don't know why I can't read it. The published ratio of 100 of your mystery phase to the ratio of 100 from the aluminum standard corundum would be this ratio. And kind of goofy though, because you would have to have some published data. Okay, so again, not very straightforward. We'll give a quick example here on Viguard's law and 1921 Viguard. And you can probably read this. This came out of an article that was published in 1991. Seems like yesterday for me. And talking about Viguard's law. And I won't read this whole thing to you, but I'll pop up kind of the important thing out of this article from Physical Review A. Viguard's law is an approximate empirical rule which holds that a linear relation exists at constant temperature between the crystal lattice constant of an alloy and the concentrations of constituent elements. And application, oh, that's it. I highlighted what I was supposed to read. So there's a linear relation between lattice parameter and the concentrations of constituent elements. So let's take a look at how this works. All right, so we're talking about Viguard, and I don't know why I drew a unicorn. Sorry. Viguard's law. So let's, and I'm not really going to calculate too much, work much out here. I'm just going to kind of show you how you would kind of use Viguard's law in a more practical sense. And so let's take the example of white gold. And white gold, if you don't know, it was a platinum replacement. And it came out in the 1920s. And that's not how you do 1920s. And again, World War II era, because platinum was used in a lot of electronics, not electronics, excuse me. It was used to make catalytic converters for vehicles. And so jewelry basically the jewelry industry needed a substitute. And so that substitute, you guessed it, gold. And in general, white gold is it's usually a white metal. And I think the first one, so they make it out of palladium and gold, not copper, because that would be red gold. Copper, nickel, no, geez, excuse me, nickel, silver, and palladium. So let's just use nickel. nickel and gold. And AU is aurum if you're into the Latin of where this elements come from. And so if you want to use Viguard's law, and we said on that previous slide that it says there's a linear relationship between lattice parameter and composition, and you can plot it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can hear me count. That's okay. I'm trying to get even dividers. I probably messed up, but and we can just say 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So this would be percent weight, or atomic percent. And in this case, we can plot nickel and gold. And so this is atomic percent gold. Okay, so gold here, nickel here. And this is going to be lattice parameter. And it's going to be in angstroms, okay? And A, lattice parameter A. And so nickel, the lattice parameter of nickel is and the lattice parameter of gold is 4.08. So let's just say this was 3, this is 3.5, and this is roughly 4. And so we can put it slightly higher. I'm trying to be somewhat approximate using my fake graph paper here. All right. And so now I'm going to do the best I can to draw a straight line on my Surface tablet here. I'm just going to try to draw it. Not bad. All right. So we won't really work anything out because it's kind of a graphical approximation if you think about it. But here 50% falls about here, and 3.52, let's just say this is 3.75. Let's just guess that this is 3.8. So based on Viguard's law, the lattice parameter of a 50-50 mixture, assuming that, you know, things diffused into some sort of substitutional diffusion type of mechanism, would be, you know, roughly 3.8 angstroms for a 50-50 mixture. And so kind of a practical use of Viguard's law. One other thing, if you do XRD, okay, and you're getting two distinct peaks, and the d-spacing of 1, 0, 0, matches either nickel or gold, and you don't see anything else, then that means you're not really alloying at all, that it's a non-alloyed mixture. And kind of an application of this type of analysis would be for like mechanical alloying, where you don't melt the materials together, you put them in like a ball mill, like a high velocity ball mill, and kind of grind them together. And then you can tell how effective you were at your alloying process this way. Anyway, again, as always, hope this was informative. Another flavor of XRD that's oftentimes used, particularly if you're working with thin films. So if you're growing something on a semiconductor substrate, grazing angle XRD would be the way to go, because you don't want to penetrate into the substrate. You want to actually be able to characterize your film. And so the tube is held at a constant angle. It's usually low, and it's usually 1 to 15 degrees. Okay, so theta 1 to like 15 degrees. It's seldom higher than 15 degrees. And we also use this attachment called a pig snout. So we don't use the slits like we've seen before. We use this pig snout, which actually makes the beam columnated, so it makes it a circle instead of a line. And so you want to be able to analyze the coating without getting signal from the substrate. You get a depth of penetration equation, and typically, again, you're kind of looking at you're kind of knowing what you're looking at. So P equals 1 minus E. I'm real sorry about the quality of this equation. This is an exponent. E to the negative 2 mu x over sine theta. This equation is taking the linear absorption coefficient. So you kind of have to know the density of your material if you don't have linear absorption coefficient data. If you look at that NIST database I pointed out to you, you can get linear absorption coefficient data. So the depth of penetration, 1 minus E to the negative 2 mu x. Typically, this units would be centimeters. It all depends on what your linear absorption coefficient data is given in. Then sine theta. And in this case, theta is theta because it's actually the emitter angle. Okay, so we're not dealing with this 2 theta business. We're looking at the emitter on this in this context. Kind of things to bear in mind when using the instrument, and by the instrument I mean the Bruker and MME. The emitter side has these slits which must be inserted as pictured, and so you read from the bottom up. And you want to keep note of which slits you use. And before the days of Lubchenco, I was running the equipment, and so several times I've had students basically tell me they can't repeat their data, and I'm like, well, what slits did you use when you ran your instrument? Would be the kind of number one question I would ask, and they wouldn't be able to tell me. And so you always want to take note of what of machine parameters. And this would be a machine parameter, and it's always good to have a lab notebook. My lab, we have our own lab notebooks, polymer extrusion lab, where we write down important stuff. And some of these important things would be, machine parameters. Which slit did I use on my emitter? What scan speed did I use? You can also change the speed at which the arms move, and that actually has an effect on your data as well. Slower scan, again, higher resolution. Faster scan, you get it done quicker, but you're losing resolution that way. The detector side also has slits, and they're this kind of dovetail thing, or dovetail shape. And a lot of times you can jimmy it so you can put it in upside down. And when you put it in upside down, you get no signal. And when you get no signal on an XRD, it appears as vertical lines on a screen. Okay, so don't forget that. And I know some of you look at the PowerPoint versions of the lectures, but hopefully you're paying attention to the video as well. Always, if you see vertical lines, that means you've done something wrong with the slits because you're just not getting any signal to your detector. The dovetail always points down, and you can vary the slit size as well. And the same thing holds true. Okay, a wider slit, you get more signal, but you also get more noise. A narrow slit, you get less signal, but you also get less noise. And if you put it in upside down, you typically get no slit at all. These slits, it's actually composed of lead, and so you don't really want to touch them. And I'm almost thinking I'm showing bad PPE habits by not wearing gloves. But there are people that say you're not supposed to wear gloves when you handle instrumentation, so I kind of argue against that as well. But these, hopefully you see the pointer. Let me get to a laser pointer. These are lead, and I admit this. I'll admit this because I admit it all the time. One time I dropped one, and then the piece fell right off, and I was very upset. I thought I had done a great deal of damage, and so I went and got what any engineer would get, either duct tape or super glue. In this case, I got super glue, and I looked very closely at it, and I could see the glue left over from the last person who had dropped it and broke it. And so these are pretty sturdy. You can glue them back together. I don't recommend that as a regular practice, however. And anyway, so slits, and part of the whole Bragg-Brentano setup. Kind of another note, non-powder specimens sometimes require creative solutions to achieve the correct Z height. And I don't know if you can see this, but we've stacked up just a bunch of pieces of metal because we're looking at a solid sample. On this instrument, it has a laser, and if your Z height is correct, the laser will form an X. There's actually two lasers that come together and form an X. So that's how you know if your Z height is correct. I kind of debate whether to talk about this stuff now or talk about it later. I always call it stuff okay to put on until electron diffraction, because you get a lot of material with X-ray diffraction. But I'll kind of go through it because that's how I roll. And so diffraction happens. I'm going to go over this really fast. We'll talk about it again with greater detail when we talk about electron diffraction. I'm going to just say reciprocal lattice diffraction spots. Reciprocal lattice is a construct we use to actually interpret patterns. I don't talk about it much here because most of what we do in modern X-ray diffractometry is interpreting spectra. For spot methods like single crystal diffraction, what applies to electron diffraction will be greatly applicable to single crystal. So if you're looking for that, just wait till we start talking about TEM. I think I'm going to go ahead and stop now and really just save it for electron diffraction. So hopefully this practical stuff was truly practical to you, and hopefully you will find it useful, not just for getting through this class, but for your research endeavors. And if you have any questions, always feel free to send me a note, ask. Hopefully when COVID's over, we'll be meeting in person soon. So thank you very much.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.